Hey everybody, the last video we are focusing on for our AP Physics 1 curriculum, at least as per 2025, is something called Bernoulli's principle. It's one of the major ideas that help govern how fluids are moving, say through pipes, and it leads to at least one kind of counterintuitive idea that is one of the major, at least factors for a lot of phenomena that we see. Now, part of this is we're going to look at application, see kind of Bernoulli's principle in action, as well as another theorem that comes from this principle known as Torricelli's theorem, okay? To begin, I actually first want us to begin by thinking about the ideas of energy. We learned about how objects have energy and how that energy is conserved. It can change from one thing to another. And to be honest, something I maybe want to spend just a moment is how we got these equations, these conservation of energy equations. If you remember, we talked about how, like when we had a simple object, and I think in one of our past videos, we just had an object that was released and it was falling. And we remember that, well, work is when there's a change in energy. We would say things like, let's assume there's no non-conservative forces doing work or anything like that. So if I just have a ball that's falling straight down, that change in energy is a change in gravitational potential. We also reminded ourselves that from the work energy theorem, the net work is equal to the change in kinetic energy. So I would maybe have something like this, and I would get this 1/2 mv squared minus 1/2 mv naught squared, pardon my chicken scratch handwriting, is equal to, when we had this ball falling straight down, we looked at the change in gravitational potential, we would end up with mgh naught minus mgh. Anyway, we would rearrange these equations and we would get the basic idea that the energy in the beginning, 1/2 mv naught squared plus mgh naught, equals the energy at the end, the mgh plus 1/2 mv squared. Those two things were equal, or said another way, like this value here was a constant, it wasn't changing. And then we could apply that to objects that were maybe going down a roller coaster, things like that. Team, we can apply the same ideas for a fluid. I can use the idea of work equaling a change in energy. I can even use the work energy theorem to look at a fluid's, a liquid or gas, its change in kinetic energy. Here I have an example of a pipe where there are multiple things changing. There is a difference in area. There's also a change in height. We could use this to look at delta UG. And team, we also know there is this link between pressure and force. So pressure is force over area. So when we use the idea and the definition of work, force times displacement, well, that means that work, which is force times displacement, that is also equal to pressure times area times displacement. All is to say, we can derive a very similar equation for fluids. There is, in fact, work being done on this chunk of liquid. There is also work being done here. There was a change in height. This fluid gained gravitational potential. Bernoulli's principle is an equation, and it is an equation that comes from conservation of energy, or, it looks like conservation of energy by analyzing the work that's done. Team, here's the thing. We are not going to go through that derivation in this video. In my opinion, it's valuable, and I'm going to have a link in the description. It goes to a nice Khan Academy article. It's kind of long, but if you want to see where we derive this equation, you could go there if you're curious. But I admit, for the sake of time, and because it's not something the AP exam is going to directly ask you to do, we're going to skip the derivation. We'll maybe point at a couple of things, but here we go. Ready? This is Bernoulli's equation as it's written right here at the bottom. I'm going to maybe change to a red pen just to highlight a couple of things. Maybe if you look at this equation, you can see hints of energy conservation. So this equation is kind of set up where it's looking at the motion of a fluid. So here we have the fluid flowing through a pipe here. Imagine, maybe this is a water hose. So water is flowing in here. It flows up, it gains elevation, and also the diameter of this pipe or this hose has gotten bigger. Okay, there is a very similar conservation of energy thing going on. Notice right here, boy, this looks similar to our conservation, or I should just say our kinetic energy, 1/2 mv squared. Notice they don't have mass, they have density. Okay, density is not the same as mass, but the reason density is there is based on the derivation, the thing that we're kind of skipping. Also notice, man, there is a kind of version of our old gravitational potential energy. It used to be mgh. Now we have the density of the liquid or the fluid times g times h. Again, where exactly these slightly different terms are coming from comes from the derivation, which we're kind of going to pass over unless you want to go to that article. There is also the pressure. This is the pressure that's right here in this section here. Okay, remember pressure is based on a force and a cross-sectional area. There's also the pressure on this end of the hose, however much force over this cross-sectional area. So this right here, this is Bernoulli's equation. It's this link between the pressure at the two sides, the speed, that's maybe one of the key things to notice, that it has the speed of the water or the fluid here, also the height of the liquid or the fluid. And there's a big old equal sign. It looks like very similar things. The energy of this fluid is conserved, or using kind of a cousin of that, we come up with this equation. And this equation is very powerful, because that means we could solve for things like how fast the fluid is moving over here if I know some of these other parameters. And also, just like energy conservation equations, a lot of times things cancel out. Like, you know, if the pipe wasn't in fact changing height, maybe we could just cancel out these two terms right here. Or if you know, or if you're given that the speed is staying the same, or heck, if the speed is 0 in one place, or essentially 0, you might cross that off. So you're not always using this giant equation with 3 terms on each side, but this is our tool that we can use to analyze the motion and maybe the height and maybe the pressure in a given liquid. Okay, what we're going to do right now is look at one example of this, applying Bernoulli's principle and getting one idea that is not the most obvious, okay? For this setup, we're going to use this scenario, which is actually the same picture we saw before. Let's say we have a hose and it's not changing height. So to be honest, team, whatever this term is on this side, it's the same as this term because there's no height that's changing. So I'm just going to cancel those out, okay? So if those two things cancel out, what I have is that P1 plus 1/2 rho times V1 squared equals P2 plus 1/2 rho times V2 squared. We're also going to say, let's say it's just water. It's the same fluid. So they don't really cancel out, but these rho terms, these densities, they are the same in each equation, okay? So that's not changing, all right? Here's the thing, and here's kind of the punchline. We learned last class, or I should say our last video, that when you have the pipe narrowing, like we have right here, this speed, this V2 increases. V2 is greater than V1. Oh man, terrible handwriting. V2 is greater than V1. We saw that in the continuity equation. I'll write it like this. V2 is greater than V1. That means something very important from Bernoulli's principle. Now looking down here at Bernoulli's principle, what we learned before is that this speed, this V2, is larger. It is a bigger value. Well, team, let's think about this for a second. If V2 is larger than V1, but this equation has to remain equal, okay? Kind of like when we would do conservation of energy. If we learned that something gained more speed, then some of the other terms maybe had to have gone down. If V2 has gone up, that means that the pressure on this side of the equation must decrease. That's the only way I can keep these two sides of the equation equal to each other. If I have a faster moving fluid, the pressure in that section, the speed of the fluid, if it goes faster in this spot over here, corresponds to the pressure in that area going down. That is one of, if not the, in fact, biggest takeaway from Bernoulli's principle is that when you have a fluid moving faster, if these other things are staying the same, we're not changing elevation, that's another variable, but if the speed of the fluid goes up, the pressure in that fluid must go down to compensate. This is one of those ideas where College Board expects you to know in the back of your hand, okay? You're not expected to derive Bernoulli's principle, but I've seen on practice multiple choice, there's a scenario where the key idea is you're told or you can deduce that the speed of a liquid is going faster there, and maybe the correct multiple choice is something about the pressure going down, okay? So it comes from this equation, but that's a fundamental idea, an important concept. When you have liquid, liquid or gas flowing through a tube, wherever the tube has the liquid or the gas flowing faster, the pressure in that container is less. Now, I got to give a little bit of a warning, team, okay? A lot of students, understandably, they think, well, wait a minute, Thrasher. Surely, if the pressure or if the speed is going faster, it should be exerting more pressure on things. Heck, a pressure hose is a good example. Surely, students say, Thrasher, the speed of the water right here is going really fast. Doesn't that mean it's applying a big pressure? And yes, but we need to understand what we're talking about. This idea of the pressure, we're talking about inside the fluid. Here, when I'm talking about the water slamming into another object, to be honest, team, that's really more of the impulse equation. Looking at how the water, and yes, water has mass, how the change in the water speed when it slams into something is affecting the force that's applied. But remember, when we're discussing inside a hose, inside a pipe, we're not dealing with disturbances. We're not dealing with turbulent flow. We made an assumption that nothing is blocking the pipe. This wall is blocking the water. So this is kind of a different application. When we say the pressure is going down, we mean the pressure within that fluid as it's traveling, not the pressure that it might slam into some other object with. Okay, that's another topic of physics that you'd be applying. Okay, I have a little animation that I want to show. I just pulled the animation up. It's kind of a little silly, but there's this pipe here, and remember, we're surrounded by air, so there is air already in this tube. This is an open tube, if you will. And you see those little blue dots, they're kind of bouncing around. There is a certain pressure because of atmospheric pressure, but these little blue dots, these air particles are bouncing around. They're slamming into the sides of the container. I have this option here. This is why I like this website. You see these little rectangular lines that are popping up? Those are indicating whenever one of those particles are slamming into the walls of the container. They're indicating the amount of pressure that this fluid, this air, is exerting. And what we're going to see is what happens to that pressure visually when the girl or the person starts blowing in the pipe. Okay, let's see. Let's take a notice. I'm going to now have them blowing through the pipe. It's kind of qualitative, but notice when they're not pushing air across the pipe, there's a lot of these bouncing rectangular lines, a lot of collisions, a lot more pressure. But when they're pushing the air in one particular direction, it's now like the air particles are more likely to go this way, not slamming into the walls. The number of collisions is going down, and therefore the pressure is going down. Remember, pressure fundamentally are those particles slamming, applying forces to the container. So I have more speed. Now this fluid is moving faster. The pressure has gone down. When they're not blowing across that pipe, now that air particles are not moving nearly as fast as a particular direction, the pressure is more. That's what this is showing, this idea, okay? Couple of examples. I know this video, and I'm sorry to say it's going to be a little longer because this idea is very important, arguably the most important topic for this fluid unit. Okay, let's look at some examples of this. So again, here I have a pipe. Okay, we see that as the air is traveling from one side to another, this pipe got narrower here. Well, remember, there's pressure. Well, the pressure is less here. The pressure in the air right here goes down. There's more pressure. There's more force in a given area. So if this was a liquid right here, maybe this was water, there's a higher level because there's less pressure over here. There's more pressure here. So that pressure pushes down, it raises this up. Where do we see this? Man, I love kind of these classic, these old school like perfume bottles. Here's a picture, it's beautiful. You would squeeze this little bubble over here and it would spray, it would push water. It would really just do this example. By pushing air very quickly across, it would lower the pressure inside the bottle. It would draw up some perfume. If you've seen these old school bottles, that's how they work. They're known as atomizers. They rapidly push air, fast-moving air. Fast-moving air decreases the pressure. So pressure down here in the bottle is more. It'll push some of that perfume up and allow you to spritz. Maybe worth noting real quick, modern like plastic plungers, that's not exactly Bernoulli's principle. In fact, this asterisk I'm having right here, you know, not everything is perfectly just using Bernoulli's principle. I'll maybe mention a couple of things, okay? Another example, man, if you play baseball, you throw a curveball. This is a little complicated. It definitely utilizes Bernoulli's principle, but there are other things involved. If I have a baseball and I throw it, so let's say it's moving to the right, okay? This ball is moving to the right, but when I've thrown it, it's rotating. It's rotating clockwise. It turns out, team, there is friction. It's tough to understand without really zooming in, but this ball, as it's rotating this way, the imperfections in the ball drag the nearby air particles. So this ball is rotating like this. Imagine zooming in, little craggly bits. They are dragging air particles. It means that the air moves faster on this side. Here, because again, the ball is going to the left in this diagram, okay, the ball is moving this way. If I said right before, oh man, my mistake, the ball is moving in this direction. Well, air that's going in the opposite speed, or seemingly, it's counteracting these craggly bits in opposition. It means the air moves slower. If I have faster air, that means less pressure. Less pressure means more force. This ball, and this is a top-down view, okay, this ball is likely to curve, hence a curve ball. That's why when you throw a ball and you want it to curve, you want that ball to be rotating so that it oscillates, or not oscillates, it changes how the air is moving around it, which could change the pressure. Okay, I've seen plenty of YouTube videos where they show like a basketball falling, and because that basketball is rotating as it's falling a great height, it also starts seemingly defying laws of physics. It starts curving as it flies through the air. It has to do with how the air is moving around the object. I don't know if you've ever been in a shower and the current seems to attack you. Well, same idea. When water is flowing down, that speeds up the air nearby. If I have faster moving air here, slower moving air over here, there's less pressure on this side. Less pressure, okay, means that there's going to be more pressure or more force. That's partly why the shower curtain attacks you. There's actually been studies on this. We think there's other things going on, like this hot water or just the water in general might kind of create a vortex. So it's not entirely Bernoulli's principle, but it surely is involved in some way. That's what happens when that shower curtain is attacking you, at least in parts. Airplanes, team, this is the one where I really want you to be careful. If you read in a textbook that the reason there's lift on a wing is simply Bernoulli's principle, that is almost certainly using a poor explanation. Bernoulli's principle can be applied, but it's often done poorly in other websites or textbooks. Okay, a lot of websites and textbooks, they say something like, imagine this plane is moving to the left on this screen, moving to the left, and they say something like, well, if the plane is moving, the air here has to, of course, travel like this, and the air down below travels. The air has to get to the end at the same time. And since the air here is traveling this curved distance, it must be moving faster. And then faster air means less pressure. That whole argument is built on a flaw, okay? It's not true that the air on the top has to reach the end at the same time. That is not a clear or obvious answer. And in fact, it turns out often when we do tests, the air is not traveling the same distance in the same time, okay? To be honest, a better explanation, in my humble opinion, is really Newton's third law. The way an aircraft wing is designed is such that as it's moving, the particles of air are slamming into the wing and applying forces on the wing. The wing is pushing down on the air, and by Newton's third law, the air is pushing up on the wind. By the design of the wing and the angle, sometimes called the angle of attack, there's not as many particles being slammed backwards, so by Newton's third law, there are fewer forces on top. That's fundamentally, in my opinion, at least maybe an easier way to explain the lift of an aircraft. Bernoulli's principle is in fact involved. It is true there's less pressure above, but it's not as simple as just saying, well, the air has to go faster above, okay? So yes, can we use Bernoulli's principle? Yeah, but how it's often done in physics textbooks is usually not quite right. Sailboats are also a similar explanation. Okay, we don't really use sailboats in commercial use, but if you don't know, you can take a sailboat and you can sail, maybe not perfectly into the wind, but partially into the wind. And that might seem counterintuitive unless you have the sail designed so that, again, really I'd argue it's easier to talk about it in terms of forces. but there is a difference in air pressure based on how the wind or how the air is moving across the sail. Okay, it's not as simply as saying, or as simple as saying the air has to travel more distance in less time, so the speed is less, but there are bits and bobs that are related. Okay, the last bit, I'm so sorry, I know this video is long. Here's the last thing we gotta talk about, and this is the last video on fluids for our 2025 and hopefully onward AP Physics 1 course. Something known as Torricelli's, or maybe Torricelli's equation. It's an application of Bernoulli's principle, okay? The application is a way to get another equation, and it includes some additional simplifications that we're gonna make. Here in this picture, what you see is this giant vat, this giant container. It's open to the air, okay? And then there's this spout here. So obviously the water level is going down slowly and water is leaving this pipe, okay? It's leaving this opening. Here are some additional assumptions. First, we're assuming this top area is far greater than the opening of this spout. This area A1 compared to this area A2, A1 is way, way bigger than A2, okay? In fact, if you remember the continuity equation, which relates speed to air, based on this, because we're assuming this opening is so big, the speed of the water at this part is essentially zero. It's in reality not exactly zero, but imagine a lake. If I had a giant lake and there was a teeny tiny little leak and water was technically leaving off the side, the surface level of the lake would be imperceptible in its motion downward. So we're going to use that assumption, okay? So, all right, so this area here is open. All right, notice it's also open to the air, and this area is also open to the air. And that means the pressure on both sides are equal. That cancels out of Bernoulli's equation. Also, because we're saying this area here is so big that the velocity is basically zero, this term is zero right here. Which means, team, we really have a more simplified equation. Rho times g times y1 equals rho times g times y2 plus 1/2 rho v2 squared. The density of the liquid is the same in all of these, so these cancel. If I simplify this, I have v2 squared is equal to 2 times g times this change in y. I have this y2 minus y1, okay, or y1 minus y2. It's the change in y, and that means v2 is equal to the square root of 2g delta y. What is this saying? I reset my slide. This is saying that the speed of the water at this location here, it's based on this change in height, this little h that's denoted right here, okay? It's based on just this height. And I don't know if you remember, but this is actually a very similar looking result we saw with conservation of energy, the speed of an object. Just one more time showing that parallel, okay? The AP equation sheet does not directly have this equation, so technically it comes from Bernoulli's principle, but College Board does reference this equation as it pertains to fluids. So knowing this simplification, I don't know if it's worth memorizing, but being able to maybe break this Bernoulli's principle down can be valuable in certain problems, maybe labs, etc. So it comes from Bernoulli's principle. It's when you have a simplified scenario of a really big and wide open container, okay, where you have a spout and the water is flowing out of that spout, okay? Anyway, that's all. I know this is a long video, but we're done. Thank you very much for watching.